Good evening, everybody, and welcome to the latest edition of Drunk Science, where I'm not actually drunk, but I am very tired and sleep deprived, and there's been studies that show that it produces the same effect after a while. So I'm here in all of my unshaven glory to talk to you tonight about sound, a topic very near and dear to my heart. Some things to understand about sound. Sound is a wave, but it's not like a light wave. Light is an electromagnetic wave. Okay, it's energy flowing through a medium, kind of like ultraviolet rays, gamma rays, microwaves, infrared rays, so on and so forth. But sound is a mechanical wave. All right, it is areas of high and low pressure passing through a medium. Okay, it's vibration passing through something, which is why you can't hear anything in space because there's no medium, there's no gas, for example, in for the vibration to pass through. So now that we have what is sound out of the way, we're going to look at how we hear sound. And I don't have my lab coat with me because I moved for graduate school and I don't feel like grabbing it. And I didn't move with my whiteboard, sadly. So we're going to do some old school paper. Haha! There we go. Turn off the desk lamp. Yeah, so this is a very bad drawing of the ear and the hearing mechanism. So what happens is sound enters in through your outer ear and it is focused in your ear canal um, until it hits the eardrum or the tympanic membrane. And then you hit this group of three bones right here, the three smallest bones in your body. The hammer, the anvil, and the stirrup. It's malleus and fancy words, things like that. And those carry those vibrations into this thing that looks kind of like a snail shell. That's called the cochlea. And there's also these three semicircular canals coming off of the cochlea, but that's more balanced. That doesn't have anything to do with hearing, so I'm leaving that off. So what the cochlea is, it's that curly thing. It's filled with fluid, right? And when those vibrations occur, the fluid moves, and it moves over these hair cells. And each hair cell corresponds to a certain frequency of sound. Okay, sound hits the ear, the vibration passes through, and it hits the cochlea, and the vibration passes through the liquid. And the vibration is going to go at different frequencies depending on what sound is going on, because each sound is what's known as a complex tone. It has multiple frequencies all at once. Simple tones, which are just one frequency, you don't really hear that in nature. You need a tool called an oscillator to do that, essentially. You have to produce it with a machine. And so these different frequencies cause vibrations in different hair cells. When they're hit by that frequency, they are stimulated, and then it produces a neural impulse which goes to your brain, and then you interpret it as sound. Yay! So you're essentially making sound out of electrochemical impulses. The actual sound vibrations aren't getting to your brain, which is kind of cool when you think about it, right? You're hearing chemicals. I'm sure there's a drug reference somewhere in there, but it's not coming to me. Hearing loss. Hearing loss is when a really loud sound or whatever causes damage to those hair cells. Thankfully, you have multiple hair cells per frequency. There is a lot of redundancy built into your body. Unfortunately, once those hair cells are damaged, they don't grow back. Okay, hearing loss does not come back. It's sad, but it's true. But then, kind of moving it into a little more practical application, because this is fun theory stuff. So we're going to talk about microphones. A very simple type of microphone, a standard one, called a dynamic microphone. There's a couple of other types of microphones, but if you're really all that interested, just look it up on the Wikipedia or something like that. If you do anything with sound, an SM57, SM58, those are really basic dynamic microphones. SM57 is built like a tank. It's wonderful. But dynamic microphone comes down to something like this, right? The microphone body, so you can hold on to it. But this is where the money is. So we have these guys right here, which are the sound waves. And I'm doing this backwards, so I can't touch things. So we have the sound waves coming, and they hit this diaphragm, right? this like flat, I think it's metal, 57, but it's this membrane, right? And that membrane is attached to this metal piston. And so when the sound waves hit it, it causes this diaphragm to vibrate. When that's moving, it's also moving this coil of wire, okay? It's moving this coil of wire which is wrapped around the piston. And this U-shaped thing is, this is a cutaway, obviously, but this thing is a magnet, okay? So we have this conductive wire, this conductive material moving in a magnetic field. Whenever you have a conductor moving in a magnetic field, you produce a voltage, right? You produce an electric flow, okay? And that's what's going on with this. You're turning the sound waves into electrical voltage, okay? Alternating current specifically. So you have an area of high pressure where it's going to produce positive voltage, and then low pressure is going to be negative voltage. It's going to bounce back and forth. And that's where analog sound comes from, because it is analogous to the waveform in the air. But I've gone on long enough, so that's just a video for you guys, because it's been a long time, and sadly updates are going to be probably pretty slow, because like I said, I'm in graduate school now, so it's the nature of the videos. So as always, if you like the videos, like them. If you want to see more, subscribe. If you have any suggestions for the next video, throw them in the comments. Always appreciated. And I'll see you when I see you. Take care.